Hi, my name is Ben, and today I will be addressing the cosmic microwave background. Specifically, I will investigate the CMB dipole, its implications on our frame of reference, and the connection between CMB isotropy and the isotropy of the universe as a whole. Firstly, we will discuss the isotropy of the CMB, including potential sources for the dipole and our implied speed with respect to the CMB. The CMB has a dipole from our perspective with an amplitude of 3.36 millikelvin in the direction of 270, positive 40, and LB coordinates. This dipole cannot be attributed to a random fluctuation in the CMB, as those typically have amplitudes of 10 to the negative 4 or 10 to the negative 5 Kelvin. An increase in temperature is proportional to redshift and thus to velocity, implying that we are moving with respect to the CMB. We know observationally that this velocity is 370 kilometers per second and that the local group moves at between 600 and 700 kilometers a second. The gravitational explanation, then, is that there exists an overdense region in the direction of the dipole, named the Great Attractor. One theory for the identity of the Great Attractor is the nearby Shapley supercluster, which is 200 megaparsecs away from us. Let us now do some order of magnitude calculations on the Shapley supercluster. With a distance of 6.2 times 10 to the 24 meters and a radius of 7.5 times 10 to the 23 meters, we can combine Hubble's law with the escape velocity method used in problem set 10 to estimate the mass. By h times d is velocity, we should expect that Shapley is at least 10 to the 48 kilos. However, this implies uniform density, which is not applicable here. X-ray observations from Proust et al. Report Shapley to be in the range of 10 to the 47 kilograms, which accounts for the density profile. However, the velocity vectors interpreted by Kosevsky et al. Predict that the Great Attractor should be just about half as large. As well, the direction of this vector field makes little sense coming from a single point object. Thus, Hoffman et al. Predict the existence of a great repeller. So this would gravitationally correspond with an underdense region and would compensate for the misalignment of the dipole with a Shapley supercluster. However, the zone of avoidance prevents observation of the Great Attractor, and the lack of matter and therefore light originating from the Great Repeller makes it equally difficult to observe. This example serves to illustrate that the CMB only appears isotropic for a static observer. The CMB will appear different depending on one's velocity with respect to it, and thus conclusions from our observation must consider the impact of our peculiar velocity. This will prove to be useful in the next section when discussing the homogeneity of the universe. Next, I will introduce the Friedmann-Robertson-Walker model, its various components, and its mathematical solutions. I will reveal through the work of Ehlers, Guerin, and Sachs that the FRW model depends on the isotropy of matter in the universe. Here we observe the derivation of the FRW model following the method of Mohajan 2013. First, we begin with the Friedmann equation from Einstein's field equations of general relativity. This equation is composed of the Ricci tensor as well as a stress tensor, which require geometric symmetry. Next, we derive the Robertson-Walker metric, which Mohajan does not cover. So firstly, we're going to take the definition of a line integral and apply it to a four-dimensional Euclidean representation with coordinates x, y, z, and the imaginary component I. We get an expression for the length of a path between 2 points on this representation ds as the integral of the sum square of the components. Then we transpose into spherical coordinates and derive a similar representation. Using some trigonometric identities and substituting for a curvature factor k and a scale factor s, we arrive with a Robertson-Walker metric formula which Mohajan uses to solve the FRW model. Now, we return to the field equation. Mohajan is able to simplify using a pressure function, reducing the problem to depend on the scale factor and its derivatives, and the curvature k. It is important to note that the conservation of momentum and energy are both assumed in this simplification, which is integral to our interpretation of the equations. Since we know that pressure, density, and the scale factor are all by definition positive, we can use the first equation to demonstrate that the scale factor's acceleration is negative, as these must sum to 0. This means that the scale factor is a decreasing function, and thus the function for s of t is bound. This allows us to assess the scale factor as a rate of change of a constant, which turns out to be the Hubble constant. Mohajan goes on to solve these equations for special cases which have important cosmological correlates, including the transition from a radiation-dominated past to a matter-dominated present from the equation of state P is equal to 1/3 density, and predictions for the end fate of the universe based on curvatures k equals -1 and k equals +1. However, this method assumes a high degree of 3D symmetry both in the Einstein field equations and in the energy momentum tensor, which is equated to 0 by the conservation of momentum. The FRW model has been derived, but it remains to be seen if this applies to reality. Ehlers, Guerin, and Sachs initially put forth that the FRW describes the matter of the universe provided that matter is an isotropic radiation fluid. They proved that a gravitational field generated by a spherically symmetric source in shear free motion must be static, and thus the FRW model's assumption of symmetry is proven for any stationary observer. So far, we have briefly discussed the FRW model and seen through the work of Mohajan how its solutions can predict observations in the past, present, and future of the universe. However, we have also come across many mathematical simplifications required by FRW, including assumptions of symmetry in the field equations, conservation of momentum, and the representation of a four-dimensional spherical coordinate system in the Robertson-Walker metric. Next, we will discuss how these assumptions have been supported and refuted, and the current perspective on universal isotropy. Let us take a step back. Basic observation of our universe, including our conclusions from the CMB dipole, readily demonstrate that the geometric of the universe is not locally isotropic. If this is the case, why is the FRW model still widely accepted? So Clarkson and Barrett point out an unresolvable caveat in the EGS postulation. That is, the observer must not be accelerating, which is evidently not the case for our location in the universe. As well, Christian and Sachs, as well as McCallum and Ellis, give that in a model of fundamental congruence, i.e. symmetry, an observer has a function of redshift dependent solely on their peculiar velocity as shown. This formula concludes that the fundamental congruence term satisfying redshift observations is not well defined, and thus it is unreasonable to assume that we are geodesic observers. They further posit that even a zero acceleration observer would struggle to prove FRW, as various field equation components require conservation not immediately applied by isotropy. Evidently, the FRW model is built upon bold assumptions. To mitigate this constraint, Stöger, Martins, and Ellis report that the universe can be nearly homogeneous given that the CMB is isotropic. By allowing a mathematically lenient FRW model, SMEs show that EGS theorems have cosmological merit and that the universe is nearly isotropic in terms of matter. However, the term almost provides difficulty, and as they acknowledge, this is not the end of the investigation. In a synthesis paper by Rasanen, he calculates that the local anisotropy of the CMB is sufficient for the deviations from the FRW model. While previously assumed to approximate zero, the derivatives with respect to position of the CMB isotropy is inherently linked to local density. Since density is inherently linked to geometry of spacetime, and simple observation of our universe shows remarkable variance in density, it is cyclic to conclude one from the other. He concludes that the isotropy of the CMB is overstated, and thus all subsequent applications of FRW models to reality must be critically evaluated. Rasanen also reveals that FRW only implies a statistical isotropy across the entire universe and makes no assumptions about the local density variation. This allows overdensities and the underdensities such as the great attractor and repeller, but reduces the applicability of the FRW model. The FRW model and subsequently EGS theorems are built upon idealistic assumptions. Clarkson and Barrett denote that a non-geodesic observer has no chance in proving FRW observationally. Stöger, Martins, and Ellis show that FRW almost but not fully holds for an isotropic CMB, and Rasanen reveals that the CMB is not sufficiently isotropic for FRW assumptions to hold. Thus, while the Friedmann-Robertson-Walker model is important in cosmological generalizations, it fails to hold under modern investigation. In summary, I have discussed the CMB dipole and the possible causes, the great attractor and the great repeller, which represent over and under densities in space, respectively. As well, I have briefly outlined the Friedmann-Robertson-Walker model, which implies isotropy in the geometry of the universe, explained its mathematical derivation, and discussed the evolving opinion on its bearing in the real world.